welcome to this lecture in applied mechanics, and we are going to start considering a series of lectures under simple harmonic motion as a new topic. So, we're going to have a number of lectures, and in this series, this is the first lecture. Okay, so now the title is we've got simple harmonic, and you've got the wave motion. So in this topic, we are going to start motion. When we are starting motion, we are just starting something that is moving. Something is moving, and we call that as motion. Now, we are going to consider a certain type of motion that is called simple harmonic. Okay, now let us start by defining what simple harmonic motion is. So, simple harmonic motion is a type of a periodic motion. Periodic motion. The periodic motion is a motion that is repetitive. That is repetitive in time. For example, the motion of the piston. The motion of the piston in a cylinder bore, if that is the piston, it has got that repetitive motion. This motion is repetitive, therefore it is periodic. For example, a crankshaft has got that rotational repetitive motion. It is always repeated. It was repeating itself in time, and the piston has got that linear. It has got that linear repetitive motion. It is always repeating the path with time. Now, we've got so many types of periodic motion. That motion which is repetitive, but for a certain motion to qualify as simple harmonic, it must satisfy certain two conditions. And the first condition is the acceleration of that moving thing must always be directed towards a fixed point in its path. That is the first condition. It is stated in terms of acceleration. In terms of acceleration, the direction of acceleration, it must always be pointed towards a fixed point along its path. And then, the second condition also is in terms of the acceleration. But this condition talks about the magnitude of the acceleration. So, the acceleration must always be proportional to the distance from a fixed point. The acceleration is proportional to each distance from a fixed point. Now, to explain the two conditions which must be satisfied for a periodic motion to be simple harmonic, let us consider a simple pendulum. And I'm pretty sure we are so much acquainted with a simple pendulum. So, let us have a bob fixed, a bob connected, a bob of mass M connected to to a rope which is fixed at one end and free on the other end. So let us displace when this pendulum, when it is in the resting position, it will be resting vertically. Now, let us apply a force on this pendulum and displace it in that direction by a certain angle, by this angle. We are going to have this situation here. And after displacing it by this angle, let us leave it. When we let it go, this mass is going to, because of the potential energy it is going to acquire when this mass is displaced, it is going to try to move back to its rest position. Okay, so this is the rest or mean position. Rest or mean position. So when we remove that force, the mass will start moving to get back to its rest position. But when it reaches the rest position, it will still have that kinetic energy. So it will go beyond this point, the rest point, and come to this point. And if the system is not losing energy, at the end of the day, it will just start oscillating between these 2 points. It will just start oscillating between these 2 points. So we are going to have that periodic motion. Now, we are trying to explain the 2 conditions that must be satisfied for a periodic motion to be simple harmonic. The first condition stated is the acceleration must always be pointing towards a fixed point along the path. So when looking at this, the path of motion will be this. If we take this as point A and this as point B, this will be the path of motion for this ball. And on this path of motion, we are having this as the mean point or the rest point, where this mass will rest when it stops moving. So now, when we displace it to this point and let it go, it is coming from rest, and it will start accelerating. It will start accelerating. So the acceleration being a vector, it will be pointing in that direction. So the acceleration being a vector quantity will be pointing in that direction. Will be pointing in that direction. So it will be accelerating until it reaches this point. And when it reaches this point, it starts retarding until it comes to rest at this point before it reverses the direction. And when it reaches this point, it stops, it starts moving back. It starts accelerating. It starts accelerating in that direction. So now, it starts accelerating until it reaches the mean. It starts to retard until it comes to rest again and reverses the motion. So now, the acceleration in this case is pointing towards the mean. When moving from B to A, it is pointing towards the mean point. And also when moving from A to B, it is pointing towards the mean point. So, for the first condition, the acceleration is always directed towards a fixed point in each path. So now, this fixed point is the mean. Is that mean point? Is that mean point or the rest point along the path of motion? Then the second point was the value of acceleration must always be proportional to the displacement from the mean position. And to explain that point, we are still going to use the same figure. Okay. The acceleration must be proportional to the displacement from the mean position. This is the mean position. Now, the displacement from the mean position is the distance from this point to whatever point. So let us say we want to find the acceleration when the ball is in this position. That in this position. So we have got this distance from this point. We have got this distance from the mean to the point where the mass is. That displacement, let it be x. So now, for this condition to stand, the acceleration mathematically, the acceleration must be proportional to the displacement from the mean point. So that x is the displacement. So if we want to find the acceleration when the mass is at this point, implying the displacement is that from the mean to that point. So that is the displacement. When we replace the proportionality sign with an equal, the acceleration is going to be equal to kx, where that x is the displacement. Now, when the acceleration is always pointing towards the mean position, and the acceleration is proportional to the displacement, then that periodic motion qualifies to be simple harmonic. Okay. Now, having stated the two conditions that must be satisfied for simple harmonic motion, for a periodic motion to be simple harmonic, let us consider the terms that are used to describe the periodic motion in general. And if I'm not mistaken, in high school physics, we did waves. And the same words which were used to describe waves are also used to describe any periodic motion. The waves are a type of a periodic motion. So to describe the periodic motion, we are going to use these terms. A displacement denoted by letter x, and then the amplitude, the stroke, the period of periodic type, and the frequency. And to define these terms, we are going to use we are going to use this figure. Let us have a rod OA that is rotating at point O. That is rotating at point O in the clockwise direction. And it is rotating with this speed W. And at the start of the motion, let us say it is starting at angle 0 and it is rotating in that direction. So, for a complete revolution, it will start from 0 degrees, reaches 90, 180, 270, and it comes back to that same position. It has made a complete revolution, and that makes 360 degrees. So now, let us say it is starting at point 0, and that is the mean position. So as this rod makes a rotation, let us trace how far point A will be from the mean position, which is the horizontal. So now, when this rod is at 0 degrees, point A will be on the horizontal. When this rod reaches this point, point A will have come to this point with this distance, between the mean position and point A. When it reaches this point, it will be at this point, having this displacement from the mean position. Now, we are going to define displacement. Displacement X, displacement as the distance between the mean position and the actual position of the particle. So, for this case, the position in which point A is, the distance from the mean position, distance from the mean position to where it is equal to this distance. So this distance at this point is x, is the displacement. Now, the displacement is changing as A changes position. So, when A is at this position, the displacement will be that. Clear? So the displacement is the distance from the mean position to where a particle is. And from displacement, we have the amplitude. Got the amplitude. Now, amplitude is the maximum displacement. Maximum displacement, we are going to have maximum displacement when point A reaches 90 degrees. So, from the mean position, we are going to have that as the maximum displacement, and that is going to be equal to A. Then, when this rod reaches 180, it will have come back to the horizontal, to the mean position. And when it reaches this point, it will be that point and we are going to have that displacement, x. So, for this periodic motion, we are going to have the maximum displacement from the mean on the upper side, and also the maximum displacement from the mean on the lower side. So therefore, this is amplitude, and also this is an amplitude. So now, when we take a look here, this amplitude is equal to the radius, of this rod that is rotating. So amplitude, the maximum displacement from the mean position. And then we add the stroke. The stroke is equal to the total displacement of a particle. So we have this displacement and this maximum displacement and this maximum displacement. When we add these, we get the total displacement for a particle. So the total displacement for the particle is the stroke. So from that maximum point to that maximum point, this total displacement is equal to the stroke, presented by S. Now therefore, the stroke is equal to the summation of this amplitude and this amplitude. So mathematically you can say S is equal to the summation of this amplitude plus that amplitude. Therefore, S is equal to A plus A is equal to 2A. The stroke is equal to twice of the amplitude. Clear? Then from the stroke we have the periodic time. Okay, so now this plot that has given us a curve is a plot of the displacement of the particle, against time. So on the vertical, we have the displacement, and on the horizontal, we have got time. So when that rod is at 0 degrees, so this is time. When point A is at 0 degrees, it is along the mean. Now with time, as time moves, the amplitude is going, the displacement is going to increase until we reach the maximum, drop, we get back to 0, increase until we get to the maximum, and as we go on, that cycle continues. Now, to make a complete circle, when we start at point 0, to make a complete circle, we are going to have a certain amount of time taken. So since the horizontal is signifying time, period is defined as the time taken to complete one oscillation. So for this guy to move from and back to 0 to make one complete revolution, that is giving us 160. When we translate this to this, it is the time from 0, that will be 360. So from 0, we reach maximum at 90 degrees, 180 degrees, then at 270 degrees, and then 360 degrees. So the period is the time taken. Is the time taken to complete one oscillation. It's the time taken to complete one oscillation or one cycle, whichever language you use. And then you've got a frequency. Frequency is the number of complete cycles. Frequency is the number of complete oscillations made in a second. Number of complete cycles or oscillations in a second. Okay, so if this guy makes 50 oscillations in a second, then the frequency is 60. So when we relate these two parameters, the period when we relate the period and the frequency, from the definition, we are going to find out that the period is inversely proportional to the frequency. So the period is equal to 1 over the frequency. When you make the frequency subject of the formula, it's also going to be that. So in a scenario, when you have the period, you can solve for the frequency, and when you have the frequency, you can solve for the period. They are just a reciprocal of each other. So, having defined the technologies that are used to describe periodic motion, which is the displacement, the amplitude, the stroke, the period, and the frequency, let us just look at where we can. Let us consider where we can apply, simple harmonic motion. Now, simple harmonic motion be applied in the mathematical modeling or mathematical designing of a crank-slide mechanism. Crank-slide mechanism is a mechanism that makes, the crankshaft, the connecting rod, and the piston in an engine. Then you can use it in the design of the spring mass systems. The springs are highly applied in machines, so we can use the simple harmonic motion to model the spring mass systems and also to model a simple pendulum. So in our coverage, in terms of mathematical modeling and doing some mathematics in simple, we are going to consider these three systems: a crank slider, spring mass system, and a simple pendulum. So, having considered these issues, we have come to the end of this lecture. So, go through this lecture and take time, especially on the two conditions which must be satisfied for a periodic motion to qualify as simple harmonic, and also the description of the simple